Securing Record Communications. The TSEC KW-26 by Melville Klein. Preface. One of the missions of the National Security Agency, NSA, is to protect classified information, whether in storage, processing, or transit. Collectively, Information System Security, InfoSec, is the development and application of hardware, software, and doctrine. The in-transit element, called Communication Security, COMSEC, assures that the underlying information is protected from external exploitation, disruption, or misrepresentation and is available only to authorized recipients. This brochure tells the cradle-to-grave story of highly successful cryptographic equipment for Teletypewriter TTY communications, the TSEC/KW-26, and the people who developed, produced, and fielded it. Teletypewriter COMSEC. The changes in communication technology leading up to the introduction of the KW-26 date back to 1907 with the introduction of the start-stop method of synchronizing printing telegraph equipment by Charles L. Crum and his son Howard Crum. Until that time, synchronous printing telegraph systems employed constant length codes, e.g., a 5-element baudo. However, these systems required very accurate means for maintaining synchronism between electromechanical transmitting and receiving instruments. Start-stop overcame this drawback by resynchronizing at the start of each character, making it no longer necessary to accurately control the speed of the instruments. Each character was assigned a unique 5-unit combination of marks and spaces, preceded by a start element and followed by a stop element. The 32 possible combinations accommodated the Roman alphabet and 6 control codes, uppercase, figures, line feed, carriage return, etc., and were adopted as an International Telegraph Alphabet number 2, I number 2. Start-stop teletype began to find worldwide commercial applications about 1920. The instrument employed a typewriter-style keyboard and printed the received signals directly onto paper tape without requiring the intermediate use of perforated tape at either end of the system. It was capable of working at a speed of 40 words per minute. For the first time, anyone who could type could send messages without needing a skilled operator, or for that matter, any attendant at the receiving end. This system was so successful that it became the dominant means of handling record traffic, but not securely. In 1917, a young AT&T research engineer named Gilbert S. Vernon, working on new developments in telegraphy, came up with a novel and relatively simple scheme for encrypting TTY. He mixed 2 baudo-coded punched paper tapes, whole being a plus, no hole a minus. One tape contained the plaintext message and the other the key. These tapes were added, modulo 2, exclusive OR, in a mechanical tape reader, producing output cipher signal. At the receiving end, the incoming cipher is added, modulo 2, with a local copy of the identical key, producing the plain text. If the key is unpredictable and flat, i.e., probability of a plus equals that of minus equals 1/2, then the cipher text is unbreakable, impervious to cryptanalysis. The Vernon logic. Vernon had invented the unbreakable cipher, one-time tape, OTT for online TTY encryption. In 1919, he was granted a patent, perhaps one of the most important in the history of cryptography. AT&T demonstrated this technique to the U.S. Army Signal School in 1918. They added 2, modulo 2, relatively prime 8-foot tape loops, making a secondary key tape of 1 million key characters. The Signal Corps showed little interest. It wasn't until World War II that the Signal Corps adopted it for high-level TTY traffic, SIGDOT. In the 1920s, AT&T marketed the Vernon system for commercial privacy applications. Though an engineering success, it was a commercial failure. Cable companies and businesses continued to use old-fashioned codes instead of secure encryption. Crum and Vernon opened new vistas for TTY encryption, a far cry from the technology of the pencil and paper codes and ciphers for hand-keyed Morse deployed at that time. A competing technology for securing TTY messages was invented soon after Vernon: the electromechanical rotor machines. Though they operated offline and were more complex devices, their operational benefits in key management considerably outweighed the production/destruction of mounds of one-time tapes. Invented by four men in four different countries in the 1920s, an American, a German, a Dutchman, and a Swede, wired rotor machines were the principal means of message security before and through World War II for governments and commerce. During World War II, the U.S. used commercial offline rotor machines, e.g. Hagelin M209, SIG-ABA, SIG-TOT with government-produced key. Lessons learned from World War II. The stunning successes of Allied cryptologists in breaking the Enigma and Purple did not go unheeded by the Department of Defense after the war. The military services undertook a concerted recruitment effort for engineers and mathematicians to develop a first-rate in-house cryptographic capability. The Army formed a COMSEC RD organization within the Army Security Agency, ASA. The Navy had a comparable organization, the Naval Security Group, NSG. The senior cadres in ASA were former Signal Corps officers and non-coms. In-house development of improved offline rotor systems to replace the World War II rotor machines was initiated. ASA also sought a high-speed online OTT equipment to replace the British 5 UCO, currently being used in the intelligence community. The British enjoyed great success with this system because, being fully synchronous, it could be electrically regenerated on tandem high-frequency HF radio links. Like predecessor U.S. equipment, SIG-TOT, it used mountains of key tape to operate on a 24/7 basis. The sheer magnitude of generating, certifying, and destroying key tape, and the cost of distribution and accountability limited their use to the most sensitive traffic. On the plus side, OTT systems provided traffic flow security, TFS, and operated directly with commercial circuits. Another inherent capability of the 5 UCO was that the operator at the receive end could maintain crypto synchronization if the path delay suddenly changed by walking up and down the key tape, one character at a time or one bit at a time. This procedure avoided the operationally cumbersome task of a restart. With the merger in 1949 of the service cryptologic agencies into the Armed Forces Security Agency and the creation of NSA in 1952, jurisdiction over U.S. cryptography was vested in NSA. This extended to major players outside the Department of Defense. Throughout, a primary objective was communications security for record traffic. Howard Barlow, chief of the Record and Data Group, initiated as a high-priority research on viability of electronic encryption for TTY, namely, an affordable, inconspicuous value-added adjunct to the user's communication system. It should not be a time or an operational bottleneck and should assure that the work factor is commensurate with the protection period. This was a decided break from past. In technology, tubes rather than relays and wired rotors. In cryptography, keystream generators rather than one-time tape systems. And in key management punch cards rather than keyless or wired rotors. To be retained in the replacement of the 5 UCO was the Vernom Modulo 2 convention and its traffic flow security, TFS, capability. The proposed TSEC KW-26 development was targeted to the above requirements, i.e., to provide TFS and message security for all classifications of record traffic. Development effort. When the requirements for secure TTY were defined, the most mature electronic technology was the miniature vacuum tube. Tubes had limitations, however, related to their reliability and power consumption. Although the transistor had been invented, 1947, it was not ready for prime time. Therefore, the search was on for an alternative solution. The RD engineers sought out leading-edge industrial partners in digital technology. The KW-26 graphically illustrated this synergism. A young engineer working in Howard Barlow's division was intrigued with the research on bimagnetic cores by a former college classmate, Lyle Thompson, at Burroughs Corporation Research Center. Lyle described how they were using multiple winding toroidal magnetic cores as bistable magnetic elements, BIMAG. With appropriate interconnections, they performed the binary logic and were used to implement shift registers. This spawned ongoing technical exchanges between the logic designers at the Research Center with Howard Barlow and members of his staff for funding further research. Concurrently in 1952, an experimental vacuum tube model of the KW-26 was being fabricated in-house under Joe Hannon, a recent electrical engineering graduate, Vern Ziegler, and 2 Army technicians. Joe's team breadboarded a proof-of-concept model based on the Dick Marsh Cryptologic and I/O guidance by Frank Mitchell, Joe's supervisor, for the plethora of communication interfaces the KW-26 would face. Charles Napier designed a novel common fill device, CFD, a first of the breed for the daily crypto variable. It used an IBM card punched in a Rembrandt format, 45 × 80 columns, round × rectangular holes. His design, fabricated in the RD model shop, was incorporated into the breadboard. In practice, the operator inserted the daily keycard into the CFD and closed the door securely, locking the card in place. COMSEC doctrine did not permit card reuse. Therefore, to meet this requirement, the card was severed upon reopening the CFD. The completed breadboard model required a 6-foot telephone relay rack for each transmitter and receiver terminal. In 1954, TECCOM, the NSA telecommunication organization, successfully tested the system on a circuit looped at an overseas site. It demonstrated the feasibility of electronic TTY encryption. The system employed the newly devised Koken crypto algorithm, used with a free-running TTY input. As the breadboard was being built and tested, Joe Hannon prepared the specification for an outside development contract. Engineering Development Contract. The Request for Proposal, RFP, was released sole source in 1953 to the Burroughs Corporation. Its objectives were to demonstrate reliable logic elements, low power consumption, controllable spurious radiation, ease of use, availability, continuous operation, in-output compatibility with associated communication systems. The RFP was based on Fibonacci-Vice Kokon motion. Their proposed cryptologic design was based solely on BIMAG, from the Fibonacci shift registers to the binary logic combining elements. The CFD was government furnished. After evaluation of the Burroughs bid from cost, schedule, and technical risk, NSA awarded the development contract in 1953. The initial design indicated that BIMAG were superior to vacuum tubes on reliability and power consumption. Though the KW-26 clock rate was relatively slow, less than 5 kHz, the vacuum tube pentodes driving the BIMAG elements were approaching their design limit. The first model was delivered in 1955. This model demonstrated BIMAG as a viable technology for the KW-26 logic. The toroidal cores of exposed magnet wire were mounted on islands along the edge of the plug-in circuit board and hand-wired while on the circuit board. Both the Burroughs and the NSA engineers recognized the next hurdle, i.e., the need for more practical packaging of BIMAG circuits in the final engineering development phase. These units also were successfully evaluated on loop TCOM circuits. A follow-on contract for final engineering development models was awarded to Burroughs in 1955 to correct the above deficiencies. During this phase, each core was packaged as a potted module with 12 I/O pins connected to 6 internal windings. Up to 80 of these potted modules were mounted on large multi-layer printed circuit PC boards. 5 of these PC boards were used in the transmitter and receiver equipment. Power pentodes were mounted on each of several plug-in packages. The Burroughs engineers also productized the CFD. Initial deliveries began in 1957 for customer evaluation. Environmental tests showed these models exhibited intermittent loss of crypto synchronization. Extensive temperature tests, up to 125 degrees Fahrenheit, revealed that the ceramic capacitors were shorting out at the higher temperatures. Erie, the manufacturer, upon subsequent testing, discovered a bad batch had been shipped to Burroughs. As a result, Erie instituted new quality control procedures, and Burroughs instituted incoming inspections. No further problems occurred. The RD project team released the final design to the COMSEC production engineers for procurement of operational equipment. In the interim, Joe Hannon and Tony Russo participated in the ongoing operational evaluation with TCOM. Operational trials. Final engineering development units were operationally evaluated on the Criticom network, the title assigned by the JCS to those communications supporting the National SIGINT mission. The KW-26 performed very well, except for the problem of dealing with transmission anomalies. They lacked the ability to walk up and down the keystream as had been possible with the 5UCO. This limitation was later overcome by inserting a 21-bit delay in an applique, TSEC HW8, between the incoming line and the receiving KW-26. Initially, the operator would set the delay at 11 bits and bring up the link. If the path delay shifted abruptly, the receive operator would search for the correct delay, thereby maintaining crypto synchronization. Garbled traffic would, of course, have to be resent. This was effective about 90% of the time, thus avoiding the time-consuming restart coordination with the sending station. NSA and the Navy purchased approximately 450 HW8s. Figure 1 TSEC HW8 Transmission Delay Compensator. Services requirements for numerous modes and speeds significantly increase the cost, schedule, and the complexity of the original engineering design. Of the modes and speed combinations possible, it is doubtful more than 3 or 4 were ever used. One option, the so-called speed normalizer, delayed the production deliveries at a time when the equipment was critically needed. This option was designed to operate via the low-speed transoceanic direct current cables, which were in their last days of service. Other costly options permitted operation through AT&T mechanical regenerative repeaters, also being replaced in the 1960s. Production. The NSA COMSEC Production Organization coordinated DoD and community buys, issued RFPs, handled contract management, coordinated acceptance tests, provided operational support, provided technician and operator training, performed life cycle spare parts acquisition, coordinated change orders, published manuals, performed key management, carried out inventory control, handled decommissioning effort. The initial production order for 1,500 for Criticom and related SIGINT requirements was awarded to Burroughs in 1957. During this initial procurement, there was continual pressure from other services programs for KW-26s. Subsequent procurements running from the early 1960s produced over 14,000 units. These were procured for Navy shore facilities and shipboard use, Army and the Air Force tactical point-to-point service, and in fixed plant environments by the Defense Communications Agency, State, and CIA. A KW-26 system, transmitter or receiver, contained over 800 cores and approximately 50 vacuum tube driver circuits, occupying slightly more than 1/2 of a standard relay rack. Most of the space in the rack and most of the 1 kW input power were required for the special-purpose vacuum tube circuits needed to provide compatibility with the multiple input and output circuits configurations. Operational use. The KW-26 was the workhorse crypto system for the point-to-point circuits of the Criticom network. TCOM also used it to provide traffic flow and content security to from SCA SIGINT sites to in-house NSA analysts. The services used KW-26 to secure their tactical torn tape and store and forward message networks. In the early days of DCA, the KW-26 was the principal encryptor for the auto-DIN trunks. CIA and State deployed them in their point-to-point circuits. Starting in the mid-1980s, the system was decommissioned by NSA, being replaced by the more advanced solid-state data encryptor, TSEC KG-84. Figure 2, TSEC KW-26C, Electronic Synchronous Teletypewriter Security Equipment. Parting lessons learned. In the 1950s, the requirements process, lacking a command decision authority within the DoD and the intelligence community, subjected the multi-user KW-26 to a plethora of engineering changes. Originally specified as a limited mode, fixed plant equipment, the equipment had to be modified during its development to handle the numerous operational modes, e.g. shock and vibration of 16-inch guns being fired aboard ship. Its developers quickly realized the need for far greater understanding of user environments in preparing specifications, as well as a better mechanism to incorporate engineering changes after operational testing. To the extent possible, the handoff from RD to production engineering should strive to be a build-to-print process. Having the ability to slave all the KW-26 transmitters in a communications center to a master clock would have been a useful tool to reduce preventive maintenance and improve availability. Epilogue. The KW-26 truly was a value-added adjunct to secure point-to-point TTY communication circuits. From an operational and maintenance viewpoint, it withstood the rigors of 16-inch guns being fired and overall experienced very few operational outages. It met the operational objectives for a diverse set of users, particularly those in the Criticom network and in the general service (GENSER) community. For over 25 years, it served the DoD and the intelligence community throughout the Cold War. Decommissioning lasted several years. NSA instructed the services and other holders of record of the demilitarization process in returning the sensitive components to the Information Assurance Directorate, IAD, or other locations for secure destruction. These were the tracks on the printed circuit boards and the CFD, which revealed information about the combining and cryptologic. The remains, example the aluminum chassis, power supply, I/O, after having their labels removed, were melted down and discarded as scrap. Figure 3. The KW-26 in operation. When the last days of the first KW-26 became apparent, TCOM sent the first units to the NSA archives for historical preservation. The parting words of the principal TCOM transmission system engineer: "I can think of no equipment that advanced the cause of secure 100 words per minute teletypewriter service more than the KW-26. It also proved that electronic online encryption was not only feasible, but actually enhanced system performance."
So that was our today's artifact. The small book, published in 2003 by the NSA's Center for Cryptologic History, as you can also see here. And you can also find a digital copy of it available for free by the NSA, link in the description. Let us know if you liked it and if you'd like us to turn more intelligence community publications into audiobooks. The KW-26 was an important part of cryptologic history, but just like many other aspects of the spy world, it's unknown outside of the small circle of the SIGINT space, despite its significant importance to national security and classified communication systems. A great reminder that nothing is as it seems.